In this lab, we're going to start looking at building finite state machines using discrete parts. And what we'll do is we will actually design a 3-bit binary up-down counter. Now, a counter is a special case of a finite state machine, meaning that it usually traverses its states linearly. But a binary counter that can go up and down also requires an input to it, and so it is a finite state machine. It is something that tracks its states and it responds to inputs, and it's kind of a neat way to get familiarity with actually designing and implementing these things. Okay, so the learning outcomes are you're going to design and implement a 3-bit binary up-down counter using discrete parts. You're going to use a push button circuit to provide the reset to your counter. So you're going to actually get a chance to design a circuit, pretty simple circuit, but you're going to have the ability to press your button and have it go to the reset state. So here's what you're going to need. Breadboard and wires, analog discovery 2, so we'll use this to provide power to your breadboard, and that's it. We're going to observe everything on the LEDs. So you'll use D flip-flops to hold the current state codes, and since this is a 3-bit counter, you're going to need 3 D flip-flops, so you'll need both of your 74HC74 D flip-flop ICs. You'll need 3 red LEDs and 350 ohm axial resistors in order to display the count. And then you're going to need your push button switch, and then I say a variety of HC74 discrete logic ICs. And this is because you are going to build the whole thing, and when you go to enter or create your next state logic, you're going to encounter that these circuits get quite large. Okay, and so this is gonna be a in-depth lab exercise. So you're gonna spend a lot of time, and it's gonna give you a lot of practice debugging and being methodical in the way that you do your design. But be prepared. This is gonna be a lot of wiring. So your deliverables are you'll go through the whole design process by hand and deliver the final logic diagram in the form of a JPEG, and then 90% of it is you're going to demonstrate this counter. Okay, so you're going to implement it all on your breadboard. You're going to observe it on the LEDs. You'll power from the analog discovery, but you'll also clock it from the analog discovery. Okay, so for your deliverable number 1, you're going to design the 3-bit binary up-down counter. Now, the first step is to create the state transition output table. Usually in a finite state machine, we start with the state diagram. But in a counter, the states traverse linearly, so we can actually just skip right ahead to the table. And so here's what the table looks like. Here's what you're going to create. You're going to write this out or do it in whatever format you want. So you're going to create the table, and you label the states. You can call them S0, S1, or C0, S1. But you're going to have we're going to use what's called state encoded outputs. So we want to encode the states of our machine in binary, and then have those state codes be the outputs themselves. And so what that allows us to do is it minimizes any output logic that we might have. So all we really need to do is build a state machine whose state codes increment up from 0, 0, 0 up to 1, 1, 1 and then roll over when a signal tells us to count up. And the signal that's going to tell us to count up is called up. So this up is the input into the system. It's the only input. We also have a clock and reset coming in, but we don't talk about them as the input into the finite state machine. Up is the input. So when up is a 1, we will count up. Okay, it'll increment by 1 on every rising edge of a clock. When up is a 0, it's going to count down. Okay, so it'll go from 111 to 110 to 101, and it'll count down. So we can skip the state diagram and go right to this table. And when we use state encoded outputs, we can also, that forces us to use a particular state coding scheme. In this case, we're going to do it in binary since we have a binary counter. So we can actually assign the state variables and fill in the table in one shot. So over here, you're going to have current state, and you're going to have an input, which is up. And then what you're going to do is I'd like you to call the state variables for current state Q2 cur, Q1 cur, Q0 cur. And then you're going to list out the state codes. And so for this first state, S0, which I'm going to call it S0, the state code is going to be 000. For this next state, it's going to be 001. For the next state, it's 010. The next one, it's 011. And I list all possible 8 codes right here for the current state in a binary count fashion. Over here, for every code that you're in, for every state that you're in, you have 2 possibilities of where to go next. 1 is when up is a 1, which will be you'll increment to the next state code, or when it's a 0, you'll decrement down to the next state code. So for every one of these state codes, every current state, you're going to have 2 possibilities. As a result, you need to list the state code, the current state codes, twice. So that's why I have 2 rows for every state code. Now, if you take a look at this first one, I have over here next state, you are going to have these next state variables, call them Q2 next, Q1 next, and Q0 next. And what you'll do is you'll just plop down the state codes. So for example, if I'm in S0, which corresponds to 0, 0, 0, and the up is a 1, you're going to go to state 1. And that code will be 0, 0, 1. If you come down here, if you're in 0, 0, 1 and up is a 1, you're going to go to S2, and that's 0, 1, 0. And if you're in S2 and up is a 1, you're going to go to S3, and that code is 0, 1, 1. So you can go ahead and fill in this entire table. And what I usually do is I do it for the up first, and then I come back and then I do it for when it counts down, and I fill in these. But you need to fill in the next state table right here. For the outputs, the great thing about state encoded outputs is that if you look at this, I want you to call the output count, and then we'll reference it as count parentheses 2, parentheses 1, parentheses 0. You'll notice something really simple. For every row in here, the output of the counter only depends on the current state. So I listed them here twice just to kind of complete the table. But notice that the output is 0, 0, 0 when you're in state 0 and the state code is 0, 0, 0. That means the logic for count 2, 1, and 0 is just wires. You just are going to take the state codes, the current state, and wire them to the output. Okay, so that's it. And so what happens is you don't even need to create logic for this. It's just a simple wire. Okay, so go ahead. The first step is to create this table, and then what you're going to do is synthesize the logic for the next states. Okay, so you need to build 3 circuits, 3 combinational logic circuits. One of them is for Q2 next, the next one is for Q1 next, and the next one is Q0 next. And if you think about how to do this, this column, well, let's do Q2 next first. This column is the output of a circuit that you need to create. The inputs to it are going to be the current state, which has 3 bits, and up, which is the 4th bit. That means you have a 4-input combinational logic circuit. The reason that that's important is because you need to use a 4-input K-map. And when you pop these in here, you're going to be faced with a quite large circuit, all right? And that's intentional, okay? This is a big circuit. It's also motivating the reason why we had to move to a modern digital design flow. But this is a big circuit. This is going to be your biggest one yet. And so you're going to circle these ones and try to minimize it, but it doesn't minimize that great, okay? Once you build that circuit, come up with the logic expression, go to Q1 next, and then go to Q0 next, and you'll build 3 logic expressions. Then I also want you to write down the logic expressions for count 2, 1, and 0. And they're simple. All it is count 2 is equal to Q2 cur. Count 1 is equal to Q1 cur. Count 0 is equal to Q0 cur. But it's important to write that down because it's good design practice to always document everything in your circuit. Once you get done with that, you will then go to the logic diagram. So you're going to draw out the logic diagram, and this is going to be the deliverable for part 1. Okay? Now when you draw this out, keep in mind that you're going to start with the state memory. So you need 3 D flip-flops to hold the 3 bits of the state code. Okay, so you're gonna have 3 rising edge triggered D flip-flops. Then the D input, they'll all be, they're all gonna receive the clock from a common clock and a reset from a common reset. But then for the next state logic, each of those 3 circuits that you created, those will feed into the D inputs of the associated D flip-flop. And then the output logic is nothing more than just wires to the output. So draw that up and then implement it. Or excuse me, draw it up and take a screenshot of it, or if you drew it electronically, just save it. But that JPEG of your logic diagram, that's deliverable number 1. Then you go to build it, and it's a big circuit, okay? Here are some guidelines for you to kind of fill in the gaps of how you build it. Number 1, you're going to power your board from the analog discovery. So you're going to need to go into waveforms and set up the output to be 3.4 volts and run it to power your breadboard. The second thing, you're going to use the arbitrary waveform generator, channel 1, to drive the clock of your finite state machine. This is a finite state machine, meaning that, or it's a synchronous finite state machine, meaning that all the flip-flops get the same clock. So you're going to bring over channel 1 of the analog discovery, and then you got to wire it to the clock inputs of all 3 of your D flip-flops, so they all see the same rising edge. Go ahead and set it up to run at about 4 hertz, so that'll be fast enough that you can see it on LEDs. The up input is going to come from one of your slider switches. Okay. Now the slider switches are used, you have your LED driver circuit on your board. If you just tie a wire into the output of the slider switch, the same node where you have that yellow or that single inline package pull down resistor, at that point that will give you either a good 1 or a good 0. So go ahead and wire that. That's going to be the up input. Now that up input may or may not be used in your 3 next state logic circuits. So that's where that input's going to come from. Then you need to create a reset line. And I want you to do that using your single pole double throw switch, and just go ahead and wire the 2 contacts, one to VCC and one to ground, and then the output will switch between them. And you want it so that when it's not pressed, you are driving in a 1 to your circuit so that it's running. And then when you press the button, it'll pull the reset line down to a 0, and your finite state machine will reset. When it resets, it's going to go to state 0, 0, 0. And so that's very important. And it's important to have a reset in a finite state machine, because sometimes it'll get off and you got to get it into a known state. So you press that button and it puts it in a known state. The outputs will be driven to 3 LEDs. Okay, so you're going to build 3 discrete LEDs, LED circuits. Same thing as usual. 150 ohm resistor in series with the red LED. Stuff the cathode of the red LED into the ground. You're going to build this thing. When it works, take a video, and that is the requirements for deliverable number 2. Now let me show you the size of this thing. Okay, so let me just show you what this may look like. Okay, so here is a breadboard of an example circuit. Okay, so you're going to notice a few things here. Here's your LED driver. Here's the button that is the reset. You've got wires coming in. This uses a little bit different contact for coming in, but the logic gets pretty large. Here's your LEDs to actually display it, but the logic gets large, and this is a challenge in debugging. Okay, so you got to follow good design or good implementation rules. First of all, build 1 circuit at a time. Make sure that you get each term working before you move to the next term. The last thing you want to do is build the entire circuit, turn it on, and it doesn't work because you don't even know where to start debugging. So for each of your logic expressions, go through and make sure that each term is working. Every AND term is working, every OR term is working, etc., etc., every inverter. So build it 1 at a time. You're going to also be faced with a challenge where you might not have the gates in here. Okay, you might have, you don't have a 4-input OR gate, so you might have to use De Morgan's to flip these around and only use NAND gates, because you have a lot more NAND gates in your circuit. But this is going to be a good exercise to get practice building circuits. Okay, if you run into problems and say I just can't converge on this, instead of 90% of the exercise being a 3-bit binary counter, you can choose to opt down to a 2-bit binary counter, up down, and that would only be worth 2/3 or 60%. Okay, so if the 3-bit can't work, go ahead and move down to a 2-bit. In the textbook, there is an example that'll walk you through the 2-bit binary up-down counter design part of it, so you can watch that. So you can reference the textbook for the 2-bit in order to design the 3-bit. If you choose to opt down to the 2-bit, the design is laid out for you in the textbook, so you can go look at that reference and then build the circuit from there. Okay, after you do this, this is a big lab. Can you design and implement a 3-bit binary up-down counter using discrete parts? I hope you can. It's a lot of work. And can you use a push-button circuit to provide the reset to your counter? This is one where I'm not actually drawing you the picture of how you're going to do this. You have to kind of look at prior lab exercises and think about what you're actually doing. So you're going to have to build this by yourself. If you can do those things, you have completed this exercise. Good luck.